Good afternoon and welcome to this webinar, Generators, Batteries, and Fortune Telling. This event brought to you by Mission Critical, sponsored by Eaton. I'm your moderator, Carolyn Fritz, editor of Mission Critical. Thanks for joining us. Today's presenters are Ed Spears, Product Marketing Manager for Eaton's Critical Power Solutions Division Raleigh, and Dan Carnovali, PE Manager of Eaton's Power Systems Experience Center in Pittsburgh, where power quality problems are created and demonstrated for training and testing purposes. Prior to Eaton, Dan worked for Westinghouse Engineering Services and APB Power T&D. He is a BSEE from Gannon University, an MSEE from Rensselaer Polytechnic Institute, and an MBA from Robert Morris University. He is a registered professional engineer in Pennsylvania, California, and Alaska, a certified energy manager, and a senior member of IEEE. Ed, a 35-year veteran of the power systems industry, has experience in UPS systems testing, sales applications engineering, and training, as well as working in power quality engineering and marketing for telecommunications, data centers, cable television, and broadband public networks. Don't forget to submit your questions, and later in the program, Dan and Ed will address as many as possible. Today's event is being recorded and archived on missioncriticalmagazine.com. And now I'm excited to turn it over to today's presenters.
Thanks, Caroline. Good morning, good afternoon, or good evening, and thank you all for joining us while we talk about application issues related to generators, battery monitoring, and UPS systems. Our discussion begins with the topic of harmonics and how harmonics play an important role in the evolution of today's modern power systems and the equipment applied in commercial, industrial, and data center applications. So I almost always start off a conversation around harmonics with this statement, which is, harmonics are not a problem unless they're a problem. So what does that really mean? When we discuss harmonics, the problems associated with that can be problems on the utility side that affects other customers, or it could be on the customer side itself, the people that are using the power. So when we look at the basic part and we deal with harmonics, we have to talk about the fact that the utilities are responsible to provide us with clean voltage, but it's the customers or the end user's responsibility not to put excessive harmonic current back in the system, because what that does is it then corrupts the rest of the system for other users. That could be the total system, or it could be a subsystem within a customer's site themselves. So the utility in the IEEE 519 standard governs the fact that at the point of common coupling, where the harmonics are generated from the load coming out to the source, the utility can only be fairly judged if the customers can contain the harmonic load within their system within the current limits of the IEEE 519. The voltage and current distortion caused by the harmonics in the system, and we talk about the loads that create these harmonics, including lights, fluorescent lights, LED lights, UPS systems, computers, variable frequency drives, all these loads that we're now calling the new normal on our systems, those all create these harmonics come back on the system. Those distort the voltage. So we're going to talk about a couple different methods of mitigating those harmonics. But first, let's talk about the actual method of how do the harmonics flow through the system. And it seems that a lot of people get caught up in the fact that it seems much more complicated than it is. But it really goes back to just Ohm's law. If you look at Ohm's law, and we think about power flowing from a utility source, the voltage that they provide us is usually, as we said, clean and 60 hertz. But then the loads that we put in the system used to all be 60 hertz loads, and the impedance of the load comes into play, and we look at voltage drop along the line with the impedance of the lines. But nowadays what we have to consider is the same Ohm's law, but think about it flowing from the opposite end. Think about the current coming back from the loads. And the more current that we add in terms of current distortion, the more that we actually cause heating problems and other load-related issues down throughout the system. So I start out with a system that's fairly clean, 60 hertz, and I inject current distortion. Without that current distortion, my voltage distortion is 0. But the more current distortion I add, the more voltage distortion I get. So as I add, another UPS, another drive, another harmonic source, my voltage distortion grows. And with voltage distortion, the second problem comes in. So the first problem is heating, and the second problem is misoperation. You have things that don't operate properly when the voltage becomes more and more distorted. Now a third thing comes into play, which is, we rely on the utility source as our primary source of power, but in fact, when we switch over to the generator, what happens is the source impedance can become significantly higher. So a normal utility source transformer might be 5.75% impedance. We switch over to the generator, and it's something on the order of 18% impedance. So the ZH here, the harmonic impedance, may be as much as 3 times the amount of impedance, and of course then with that, the voltage distortion grows significantly. And as that voltage distortion grows, we have problems with other loads in the system. So it may not even be the load that's creating the harmonics, the drive, the UPS, the other load that's creating the harmonics, but other loads in the system that gets, has issues with that. So which comes first, the chicken or the egg? Is it really the voltage distortion that causes the current distortion or the current distortion that causes the voltage distortion? Well, what we just talked about was the current distortion actually flowing back from the load back up to the source, and it's an easy way to think about it that way. That's what causes the voltage distortion. So as we get more and more voltage distortion, we have more and more potential for misoperation, and that's why the utility companies care. It's not that they don't care if you screw up your own system with a lot of current distortion and the issues related to that. What they really don't want you to do is screw up the primary voltage on the incoming source, because then your neighbors or their other customers will complain about it, and then they have to deal with it. So the amount of voltage distortion depends on the system impedance and the amount of distorted current pulled through that impedance. If either one increases, then the voltage distortion will increase. So once you look at harmonics, again, harmonics are not a problem unless they're a problem. Well, what is your harmonic problem? Is it a voltage problem? Do I have misoperation of equipment? Is it a current problem? Do I have heating of equipment? Is it an impedance problem? Do I need to change out some of the components of my system? There's solutions for every problem, but first you have to understand what the problem is. Here's an example of 2 transformers. One is a standard transformer on the left, and the other one a harmonic mitigating transformer on the right. The one on the left, you can see with the infrascan, runs extremely hot. And you can see it's all throughout the windings, not just in one point on the windings, but it's all throughout the windings. So as an example, a grade school or a high school, somebody donates 200, 300 computers to the school. They put all those computers in the computer lab, and in the electrical closet, the transformer that was a standard transformer wasn't designed for this heat, starts to burn up, starts to heat up. That transformer will only live about 3 to 5 years, and then all the insulation will start to crack, and then it'll break down and electrically fail. The transformer on the right runs significantly cooler, that harmonic mitigating transformer, and it can deal with the harmonics, and it can actually run more cool with the harmonics running through it. But the fact of the matter is it costs more money. So it's either a capital expense budget or an expense budget over time that people have to deal with when they're dealing with harmonics. So they have to decide, do I want to spend more money up front, or do I correct the problem over time, or maybe derate the transformer? Now with generators, this is actually an example of 4 variable frequency drives running in my experience center where we run here in Pittsburgh. But I basically have the same load on the utility source and then switch over to generator source, and you can see the significant voltage distortion. So it goes from about 4.4% to 13%. Again, the reason is that the impedance of the generator is about 3 times as much. So it follows that just with Ohm's law, voltage distortion equals current distortion times harmonic impedance. So the harmonic impedance is 3 times as much. The voltage distortion is 3 times as much. And this becomes problematic, and it has been a problem over the years with many large systems, data centers, and otherwise that use harmonic producing loads, including older technology UPSs. So here's an example of a older technology UPS. This happens to be a 12-pulse UPS, and you can see the notches on the left waveform here when that UPS was running on the generator. With the generator running and a significant load on it, you get this amount of voltage distortion, which would correspond to a current distortion if you looked at the current waveform. Now what happened in this case was they had paralleling switchgear, so they had an unloaded generator that was trying to parallel with his loaded generator, and the loaded generator distortion was so significant that every one of those notches created a little impulse on the synchronizing relay. So when they had a sync check voltage across those notches, it looked like there was something wrong and they couldn't parallel the two generators. So now you have to run all of your load on one generator instead of sharing the load between two. A couple different solutions for that. One would be to change the technology in the UPS, and Ed's going to address that, and I'll address it a little bit here. But the other way that we did it, sort of a Band-Aid approach at that time, was just to clean up the synchronizing voltage with a smaller fix, or cleaning up the actual sync check voltage. Now, I say it's a Band-Aid approach because we were very careful to make sure that we were still able to synchronize and not shift anything out of sorts, so that when we did parallel these two generators, they didn't blow each other apart, because that could have been obviously very problematic. So we looked at it and we compared the two, and we made the decision that a short-term Band-Aid approach would work, and then we looked at other methods of reducing the overall harmonics in the system. This slide basically talks about the way these old technology UPSs worked. Was they had on the utility source, they would have a certain amount of voltage distortion, and then you switch over to the generator source and the voltage distortion would be more. But you also see two things here with the generator source. One is the harmonic filter on, and the second is with the harmonic filter off. The harmonic filter on the front end of these old technology UPSs was there because we knew that they were generating harmonics. And again, we had to control that harmonic current before it went back up on the utility source, affected us or affected our neighbors. So that harmonic filter would be in place. Now, a lot of times those filters were turned off if they were below, say, 35% load, because there was issues related to that on either the UPS having issue with it or the generator itself having issue with it, because primarily that UPS filter looked like power factor correction at 60 hertz, and it drove the voltage up and caused potentially issues with the generator. So that was a problem, and as we moved forward to today's technology UPSs with active front ends, we removed that filter and the transformer in front of it, so made them smaller and lighter, and actually helped make this system much less of a harmonic contributor to the system. And oh, by the way, taking away a harmonic filter and a transformer allowed us to do it at a cost very similar, or even in some cases better, than we used to do it with the old technology systems. Now, as far as what people used to do with harmonics, and still do today in some cases, is that they oversize the equipment. It's sort of, again, it's a bit of a Band-Aid approach, but it's putting on some additional capacity so that you can withstand the amount of heating or misoperation that may occur. If you look at the top left, oversizing the generator. If you took a 1,000 kW generator and a 1,000 kVA transformer and you compare their impedances, again, it'd be about a 3-to-1. So if I take that 1,000 kW generator and make it a 2,000, now my impedance is half on the 1,000 kVA base. So instead of going from 6% impedance to 18%, I'm going from 6% to 9%. Not horrible, but still not as good as it would be on the utility source. Bottom left, we have oversized transformers and 2 times neutrals. So we did some things there to, again, live with the harmonics, the third harmonics, especially on the double-sized neutrals. K-rated transformers, in fact, were essentially like taking a 112.5 kVA transformer and putting a 75 kVA nameplate on it. So you're living with the harmonics. Top right shows that there's a little bit of losses, 1 to 2%. And if you can eliminate those losses, the bottom curve shows the efficiency curve of a transformer with losses. The top curve shows, with harmonics, the top curve shows the efficiency without harmonics. So we can eliminate a little bit of the losses in the system. And then the bottom one shows that at about 60% loading, your transformer is using 100% of its heat capacity. So again, damaging potentially those transformers over time. Now today's modern UPSs, like the 9395 and 93 PM, use an active rectifier. So it's almost like having an active filter built into the front end and basically taking a 6 or 12 pulse front end and making it look nice and clean. The other thing I don't show here, but you could also do, and we do, is put the power factor right on unity, so we can control the power factor in the harmonics. So the industry is driven towards these solutions, and just so happens with the UPS, it's also a very economical way to do it. With the loads themselves, what you'll see in data centers specifically is that the power factor corrected power supplies are now replacing what was the switch mode power supplies. So the switch mode power supply on the left had a significant amount of distortion. The one on the right, not much at all. In fact, it looks very much like a 60 hertz waveform. So, first polling question. Why? What I'd like to do is have you answer this question, and we'll talk about it briefly. But why do older UPS systems need to disconnect their harmonic filters at light load? I talked a little bit about this, and I'll let you guys answer, and then we'll see. We'll see what everybody thinks. Again, in most situations, and it looks like we're getting a pretty good mix of both answers, and I think it really is. It is a combination of both. So people have seen issues with generators, and people have seen issues with the front end of the UPS, and they're absolutely related. So it looks like we're getting pretty close to, we're leveling out here a little bit. I'm going to move to, so what we'll say here is basically that the UPS load on the generator becomes capacitive, absolutely, and the generator's capacity is limited by that. And the, the kilowatt value is limited to a certain amount, but if you go too far leading, we have issues with regulators and also the capacity of the generator itself. And then the other problem is that as you push that voltage up on the generator or on the utility source even, we can raise the voltage, and the voltage on the input of the UPS can become problematic. You might actually put the UPS into its double conversion mode if the voltage goes too high and it thinks the voltage is out of sorts. So with that, I think I'll turn it over to Ed. And
thanks, Dan. I'm Ed Spears, and I work with Dan at Eaton. And I wanted to talk with you folks a little bit about generator interface and proper sizing when you're sizing a UPS with a generator. And we'll advance to the next slide, which shows us another one of those examples of waveforms that you see with older style UPSs, in this case with a 12-pulse rectifier. That's the waveform on the left. The red waveform is the distorted current. And if you look closely at the blue waveform there, you see the notch and ring style distortion that was very common there. The current total harmonic distortion was around 12%, and it needs to be down around 5 to 7% in order to be acceptable. So the waveform on the right shows what we do, we meaning most vendors now in the UPS arena. We use an active front end or an active rectifier. And what this does in short is it forces the UPS to draw its current in a sinusoidal wave shape rather than a highly distorted wave shape. We use pulse width modulated techniques in order to have the UPS draw current in many small sips as opposed to 6 or 12 big gulps per cycle. And while we're forcing that current to be as sine wave shaped as possible, we also aligned that input current, the red waveform here, along with the voltage, so that the power factor, which is the cosine of the phase difference between the two, in this case, the difference between the two is 0, and cosine of 0 is 1. So that's how you get the high input power factor that you see on modern UPSs today. So what's the point of all this? Well, the idea is that the UPS system looks as much like a plain old resistor or a heating element or a light bulb to the source that feeds it. So instead of being a difficult, nonlinear, rapidly varying load on a generator, for example, the UPS is much more stable, which allows the generator to support it much more effectively and efficiently. So the next slide here shows the typical layout that I'm sure most of you are familiar with, where the generator feeds the UPS. And you can see a little block diagram here with the utility incoming power and the generator. The ATS is the automatic transfer switch. And then we're feeding one of the two sources, either the genset or the utility, into the UPS input. And the automatic transfer switch will typically have a set of auxiliary contacts that communicate its status to the UPS. So what that means is the UPS will know if it's being fed by utility power or by generator power. Why do we care in the UPS? Well, if we know we're being fed by generator, we may adjust our total harmonic distortion canceling effects in order to optimize for the generator. We may also limit or delay our battery recharge ability until the generator run is over and we're running back from utility power. So we don't use valuable diesel or natural gas in the generator to recharge the UPS batteries. We delay that until after the power event is over. So these are common techniques that you see now. And the benefit here for the end user is they don't have to oversize their generator as much as they did back in the olden days. If we look at the next slide, there's a table that shows that for most modern UPSs and generator sets today, here it comes. And this table shows at the top, shows the way it was done traditionally with an older UPS and older generator. And as a result, you see that in many cases, it was necessary to make the generator from 2 to 2.5, sometimes even 3 times the size of the UPS that generator was supporting, plus all the other ancillary loads that you might be powering in the building, like air conditioning and elevators and emergency lighting and that type of thing. So as we know, that was not a very cost-effective way to make sure a UPS and generator got along and interfaced properly. So these active input techniques that we described on the previous slide now take us to the middle row in the chart, where today the typical recommendations for generator oversizing for a diesel generator and a modern UPS is going to be a ratio of about 1.1 to 1 or 1.25 to 1. Now, what does this ratio mean? What we're comparing here is the rating of the generator to the input power drawn by the UPS. So if I have a 100 kilowatt UPS, a 1.1 to 1 means I can have a 110 kilowatt generator. Well, not exactly. I'm comparing the generator's output rating to the input power drawn by that UPS, which is going to be a little bit more than 100 kW due to the inefficiency of the UPS. So the things to compare for this ratio, when you see these ratios, is we're comparing the output of the generator to the input power of the UPS. Now, suppose you have an application where I have a large building like a hospital or a large data center, for example, and I have a humongous generator out in the backyard, and I'm dealing with a relatively small UPS, where the UPS is maybe less than 15% of the size of the generator. In those cases, we almost always find it unnecessary to do any kind of sizing there. The disparity in size, the UPS is so much smaller than the capacity of the generator that it doesn't cause a problem. So in the case where you have a very large generator, very small UPS, it is unlikely you'll need to pay much attention to sizing in that case. Keep in mind that we are seeing more and more natural gas generators, and it sometimes can be very variable in how those generators perform running on natural gas, whereas diesel is a little more traditional, but also more expensive and more of a environmental concern. So you will be seeing more and more natural gas generators, even the very large generators. So if I'm a data center operator, for example, and I want to know how to, or what features are important in the generator, the kinds of things that you should consider, I'll just list a few of them here. One of them is an upsized alternator, going to be a little more able to handle the kinds of distortion that the generator would see with a UPS load. The next item shows an electronic governor, but keep in mind, we have seen applications where a mechanical governor worked better than an electronic and vice versa. So we recommend discussing this with the generator vendor to see what their recommendations are before you make a decision. Other things like a coolant heating jacket in cold environments to make sure that generator starts as quickly as possible when it's needed, and of course commissioning and training by actual experts. The generator distributor will likely have well-trained people that can come out and do the commissioning and make sure everything is set up just right. Now, the same idea for the UPS. What kind of UPS features are important to make sure that the UPS and the generator work happily together? Well, the first one is this thing we've been talking about that we call an active or an IGBT rectifier. And IGBT simply means the type of transistor that's used in the rectifier, which acts as an active harmonic filter. Another important one is walk-in time and rate. In other words, if I have a big UPS on my generator and the UPS begins to accept the generator as a load, I don't necessarily want to land the entire UPS capacity on the generator instantly. I want to gradually walk in the UPS so that it doesn't stress the generator and doesn't create a transient for the generator's output load. So one of the things I can do is adjust the UPS's walk-in time from, say, 5 seconds to 30 seconds or a minute or more. I can also adjust the rate. How fast does it walk in and how quickly does it draw power from the generator? Suppose I have multiple UPSs on a given generator. If I have 3 UPSs on my generator output at the same time, I don't necessarily want all 3 of those UPSs to draw a big slug of power from the generator at the same instant. So while the generator is running, if the UPSs need to start, you can program them for sequencing so that there's 5 to 15 seconds delay between the startup of UPS 1, the startup of UPS 2, the startup of UPS 3, etc. The automatic transfer switch, or ATS, aux contact capability, so the UPS knows which type of source is feeding it. The ability to delay battery recharge, adjustable synchronization limits for frequency, time, and slew rate. And slew rate, if you're not familiar, is how fast does the frequency change, or the rate of change of frequency there. So I'm going to delay just for a moment while we refresh the screen here. In the meantime, if the moderator would go ahead and push the next slide, which I believe is going to put us on slide number 21. And when I get back in play here, I'll go ahead and resume pushing the slides at that point. So the next slide should have a heading that says the UPS can automatically correct harmonics while maximizing efficiency in eco mode. If you're familiar with modern UPSs, most of them do offer what we call an eco mode or an energy saver system. Now, in this case, the UPS is frequently operating with its static switch conducting, and the power comes from the utility straight through the UPS and directly to the critical load that we're supporting, and as a result, there's very low losses and very high efficiency in the UPS. So that's very beneficial and very desirable. However, consider the case where you may have a critical load in a data center, for example, that is very harmonic rich. Now, normally the operation of the UPS on the front of that critical load will act to cancel harmonics and basically isolate the source, whether it be the utility or the generator, from that harmonic rich data center load. However, if I'm running in eco mode, those harmonics that appear on the output of the UPS can reflect backwards through the static switch and now appear on the input of the UPS, which is the utility source in the building or the generator in the building. So thoughtful customers might think that through and say, hey, that could be a problem. And it simply, it quite possibly could be a problem. So what can be done to take advantage and get the best possible efficiency of the UPS system and still be able to correct those harmonics? Well, most UPS systems, when they're in eco mode or energy saver mode, have part of their power conversion circuitry that's in a standby status. So rather than let that circuitry sit there like so much scrap iron, we actually use that circuitry to act as an active harmonic corrector, like a giant pair of noise-canceling headphones. And if you're familiar with those, you know they'll sense the objectionable noise, and they'll quickly invert it 180 degrees and re-inject it into the headphone speakers, effectively canceling out the undesired noise of a baby crying on your airline flight. The UPS can do exactly the same thing, except at a much, much higher wattage level. But the result is we can use the suspended or the unneeded power conversion stages in the UPS while we're in eco mode to correct harmonics so that you can take advantage of the high efficiency and not have to worry about problems interfacing with your generator, etc. Okay, moving to the next slide. This shows a rather busy picture of the way this harmonic reduction system works. So it may be a little difficult to see on your screen because it is dark, but remember this presentation will be available to you to download for your own use. And if you have the time and you want to take a look at this information, what this is showing here is a distorted signal being reflected back through the UPS from a harmonic-rich load. The voltage distortion is unacceptable, as is the current distortion, as Dan explained. And when the action of the harmonic mitigation system takes effect, it only takes about 15 cycles or 1/4 of a second to bring that current and voltage distortion back into acceptable limits. So it's a very flexible and an adaptable option that is available on some large UPS systems out in the field. Okay, we're going to change topics a little bit to the battery because regardless of all this generator interface discussion, the battery has to be there and work properly in order to bridge the gap between the loss of utility power and the UPS or in the generator startup. So this brings to mind the topic of external battery monitoring. Most, if not all, UPSs will monitor the battery string voltage and let you know if it gets too high or too low. Some of them will actually perform a battery test once every few weeks or once a month. But again, that's not quite as granular as some clients like to see. A lot of our clients have very large investments in batteries, and they want to know everything they can about every battery in the system so that they can feel comfortable that when they need that battery, the capacity is going to be there. So battery monitoring systems can be added to existing battery systems, and they prevent unplanned outages. They reduce cost and wasteful practices. They should extend the battery life if it's a properly designed system, and also improve the safety for the people that are working around the battery. Let them know if an unsafe condition exists, and make sure that your large industrial battery system meets regulatory compliances. And we'll talk about those as we go through. So moving on to the next slide here. The causes of batteries failing prematurely, there's several of them here. I won't drag you through all of them. But loose intercell links or loose connections on the battery, a lack of battery maintenance. In red there you see the big one, which is thermal runaway. And many of you, if you've seen this happen, it's a pretty dramatic event. Basically, if I have a large industrial battery that for some reason, maybe it's due to overcharging, maybe it's ambient over temperature, but the battery gets a little bit warm. And when the battery starts to get hot, it draws more current. Well, when the battery draws more current, that makes it get hotter, which makes it draw more current, which makes it get hotter and draw more current and get hotter until the next thing you know, you have a fire. And this is a definition of a bad day in the battery world. So one of the primary reasons for having battery monitoring is to detect, mitigate, or prevent thermal runaway conditions. The other kinds of things you see are installation errors, improper charging, excessive battery cycling. If you have an environment where you're running on batteries multiple times a day, every day of the week or the month or the year, that's going to have a very negative effect on battery service life. And of course, there's infant mortality. When a new battery is put in, it's possible that one of the jars or cells has been damaged in shipping or has another problem that causes it to fail early on. Okay, so how can battery monitoring systems help with this kind of thing? Well, the next slide shows a definition of the International Fire Code 608.3, which describes thermal runaway, what it is for a valve-regulated lead-acid or VRLA battery, and also true to some extent for lithium batteries that are beginning to show up on the scene in a lot of UPS applications, especially within the last year or so. The purpose of detecting and mitigating thermal runaway is to reduce the risk of a failing battery causing a thermal event. In other words, a fire or an explosion. So the fire code enforced in many parts of the country is basically going to dictate that if you have a large battery system, the user is responsible for ensuring that that battery system has a method to detect and mitigate conditions that might result in a thermal runaway. Okay, so the next slide shows an example of what would be visible on the computer screen for a battery monitoring system. And you see here, it's just a page that has, in this case, 40 green blocks. And each green block represents one battery in a string of 40 batteries, 12 volts each, that's 480 volts. And if they're all green, you can go on and concentrate on other tasks. If one of them is yellow or red, it needs attention, and simply by mouse overing or hovering over that block, it'll tell you what's going on. Is it too hot? Is its impedance too high? Is the voltage out of limits, etc.? So a quick way to see the status of every battery in every string or battery cabinet that you may have associated with your UPS. On the next slide, we see an example of a discharge graph. And what this graph is showing, the blur of blue lines toward the top of the graph, is showing the discharge pattern, the voltage discharge of all 40 batteries in the string. So it's a bunch of blue lines mashed together. And if they're all pretty much marching in lockstep, then that's a normal discharge. So you see at the left-hand end of the curve, looks like a hockey stick there. You're starting with the open circuit voltage of the battery, and as the discharge progresses, the voltage falls rapidly for a few seconds, but then steadies on and begins to slope gradually towards the right-hand side of the screen. But what's of interest in this picture, if you look underneath the blue blur, you see that there's a couple of lines that are falling quite a bit faster. Those are individual batteries where the discharge voltage is falling much faster than expected, and those are the ones that may not have actually, frankly, failed yet, but need to be watched in future because they are the weakest batteries in that string. So this discharge graph will be stored for every battery discharge that occurs and kept on a server somewhere as part of the battery monitoring system, so the user can have valuable information for every battery in the system and how that battery performs. The next slide shows an example of rising battery impedance. One way to know if the battery is going to perform for you when you need it is to do a practice discharge. But the more you do that, the more of service life you take away from the battery. So most clients don't want to discharge their battery once a week, for example. But by measuring battery impedance, it gives us a very good indication that that battery's capacity is either present or absent. So again, you see now a group of orange lines at the bottom of the graph, which is the impedance of all 40 batteries in that string. And if you were to look at it over a long period of time, you would see that altogether the impedance is rising slowly as the battery ages. But look in the top half of the graph. You see there's several batteries here where the impedance has risen very quickly, and that's a bad sign. That means that cell is actually failing. And then you see the curve drop back down into the orange range. That's when that battery was replaced by the user. So the impedance drops immediately back into the acceptable range. So this kind of thing allows you to track the battery's performance over time. I think the next slide has a similar graph here showing the history. And again, we're looking at a lot of batteries during quite a few months of their service life. And you see the orange area at the bottom of the chart is sloping upward over time. And basically it's showing that over the aging process of the batteries, it is common or normal for the impedance to rise slowly over the 5 to 7 year service life in a UPS application. If the impedance rises quickly, like the one red line that you see there, that's evidence of a failing cell. So lots of good information can be gleaned from battery monitoring systems. This is just one example of several battery monitoring systems that operate similarly and provide very similar benefits. It also allows the user to take a look at their return on investment for this kind of thing. Are they able to save a couple of battery PMs? Are they able to save a disaster where they need that battery to perform and it doesn't because it didn't have the appropriate capacity? If you're doing battery PMs twice a year, that means there's only every 6 months where you know that the battery is going to perform. In between that time, the battery could weaken or even fail, and you may not be in a position to know. But with a third-party battery monitoring system like this, you can have instantaneous information about the status of that battery and have it come directly to your email or cell phone if anything is trending in the wrong direction. So here's another polling question for us, just like we did before. And we're really interested to know from our user base what's their understanding of the best benefit of a battery monitoring system. One item says, is it the proactive notification that something is trending in a wrong direction, as we said, so I'm warned in advance of a battery failure. I'd much rather fix that during a maintenance window than wait until after the battery doesn't function properly. But the other possibility to invest in a battery monitoring system may be to provide real-time insight into that battery's performance. If I'm the user, I spend a lot of money on that battery system, and I need to know if the battery is being mishandled. If someone set the charger voltage too high, if the temperature is too high or too low, how is that battery performing on a day-in and day-out basis so that I can make changes before I do damage to the expected service life of that battery. Okay, moving along to the results. Looks like we came out with about a 50-50 variation there, which is what we expected. And then we move on to the last segment of our presentation here, which is the one we called fortune telling. But our marketing folks like to call it predictive analytics. And what this does is allow us to do some prognosticating on the performance of a critical UPS system supporting a mission-critical load. So what is predictive analytics? Well, here's a good example. This happens to be GE Avionics. And if you are flying in a jet to your next location, maybe on vacation, hopefully, not on a work trip, you would much rather know in advance that the jet engine is going to fail rather than find out about it after it fails. And quite frankly, that's the way we've done things in the UPS business for far too long. It was a break-fix kind of thing. It broke, we'll tell you about it, and send someone out to fix it. What we want to change this to is more of a predictive benefit where we're able to use machine learning, predictive analytics, big data, the Internet of Things, all those buzzwords to basically get a good idea of how much risk is present in your critical power system as it is operating today. Now, we have to be careful here as a vendor of this type of equipment. You cannot predict when a UPS is going to fail, just like you can't predict when an earthquake is going to happen. But you can tell when the risk of failure becomes unacceptable. Now, you're walking a fence here. You don't want to have the computer that does all this act like the curse of the Catwoman and says your UPS is going to fail in 48 hours unless you send us some revenue. That's not going to work. But on the same frame, you have to be very careful that you do not miss something that's trending in the wrong direction that would be important. So if we're going to offer this kind of thing as an industry, then we have to be very careful to make sure that it does provide the intended benefit to the end user. So we basically get back to sensors. Traditionally in UPS systems, we might monitor 10 to 20 critical alarms and data streams from the UPS on a day in and day out basis. In order to do what we want to do here, we find it's going to be necessary to monitor some 300 different data points or data streams so that we can gather a great deal of information from a lot of UPSs that are actually operating in the field and start to put together a data analysis package that will help to predict what's going to happen. So here you even see tools like IBM Watson, which are ideal for and designed for the artificial intelligence necessary to start down this path. So these predictive and cognitive tools can lead to reduction in unplanned downtime, which is extremely important. Also, lower maintenance costs. If I can do maintenance during a predefined window rather than as an emergency after a failure, it's going to cost a lot less for the end user and for their enterprise. So the way predictive analytics works is the first thing that we do is we collect and integrate lots of different types of data. There's structured, unstructured, streaming information, information at rest, for example. Just a huge pile of data comes in to the computer that does this analytics, and it is parsed and basically organized to generate predictive and statistical models, which now give us some insight into what's going to happen with that UPS system based on what has happened in the past with thousands of UPS systems under similar conditions. If I have a UPS, for example, that's had a temperature rise of X degrees C over a certain period of time, I can compare that with other UPSs in the field to say if I see a temperature rise on this bus bar at this ambient temperature rate in this period of time and compare that with 400 other UPSs, I can get a good idea if I'm actually seeing a connection that's working loose or a normal temperature rise under load change and that type of thing. So we get the alerts out to the user, but we act on those insights and eventually automatically so that we can provide prior or predictive information on what is likely to happen to the UPS. Now, does that mean the computer is going to handle your UPS maintenance from now on and you or anybody else won't have to mess with it? No, that's not it at all. There's still going to be a human being in the process. But as you can see on this slide, UPS systems have mechanical devices like fans, air filters, contactors, and also other products that are similar to the tires and brakes on your car, like capacitors, batteries, power module electronics that are somewhat consumable and are the most likely items to fail. So we need to be able to gather a great deal of data about those devices to make sure that we can come up with a reasonable scenario as to how it's going to perform over the next short or long period of time. 40% of UPS failures are due to parts. The remaining 60% are due to human error or, heaven forbid, design errors of that type of thing. Okay. So what about this human interaction that I mentioned a little bit ago? The way this is going to work, at least for the near term, is that there will always be a human being in the chain between the predictive analytics engine and the end user, just as a sanity check to make sure that we're not producing false alarms or missing things that are important. For example, in a UPS application, you might see something like the UPS indicates that it has a fan that speed is slowed down. We use tachometers and fans now, so we know when the fan slows down, possibly due to a bad bearing. But before that goes directly to the customer to schedule a maintenance, it's going to stop at a real field service expert who's going to look at the records, and maybe he or she finds out that they replaced all the fans in that UPS only 4 months ago. So is it likely that the bearing is failing in that fan, or is it more likely that something's blocking the fan? The air filter may be dirty, the wire harness that powers that fan may have an integrity problem, or the circuit board that passes power to that fan may have a problem. So that person is going to look at all the possibilities there and decide what's the correct course of action. At the very least, if we come out to service the machine, we will not only bring a new fan, but we'll bring a new harness, new boards, and a new air filter to make sure that the fix happens on the first time out and not have to come back later once we find out what the real problem is. So a lot of benefits to this kind of thing. And as a result, predictive analytics have the capability of not only indicating device health, but also failure probability. And for the end user, the important thing there, what they want is to reduce unplanned downtime. In other words, increase the availability of what's going on in that data center. But also we have the ability to lower maintenance costs, less emergency maintenance, more scheduled maintenance, less throwing parts at a problem, and more having the right part to fix the exact problem based on a wealth of data and knowledge that we have about those conditions. As a result, we can extend asset life, we can increase the resiliency of this critical part of your power system, and of course provide greater peace of mind. Okay, so at this point, I think we're ready to open it up for questions, and both Dan and I will be on the line to answer any questions that you may have.
Well, thank you, Dan and Ed, for a great presentation. And now our presenters will address some questions that were submitted throughout the program. Okay, let's see. Can you add monitoring to generator starting batteries?
That is correct, and it's a great question. If the start battery on the generator is not functional, then that generator is definitely not going to start unless you have redundant batteries, which are a good idea. But almost all battery monitoring systems allow you to run a line or a sensing line out to that generator start battery. So just like any other battery in the UPS, the generator battery is monitored and evaluated for its performance. Now, it may be a fair distance to where the generator is located, so there may be line boosters and things like that that would be put in series, but that is a good idea. It's heartily recommended and a good question.
Are transistorized active rectifier UPS designs more sensitive to incoming power surges?
That's definitely a concern and was a concern 10 or 15 years ago when we first started using these. One of the benefits of the old style UPSs that use silicon control rectifiers or SCRs was the inherent ruggedness of those semiconductor devices. And when we switched to transistors, the first thing we had to have is big enough transistors that would handle the current and switch fast enough and do so reliably enough. But there was a reasonable concern that if I have a lightning strike with enough potential energy to jump 20,000 feet from the cloud to the ground, and that gets inducted into my building electrical system, is this active front end going to be able to handle that without problems? And so one of the things we do in the design, for example, is you will always see series inductors in line with the input circuit and other surge protective devices built into the UPS and the UPS's sensing circuits to make sure that we have every bit of the robustness and resistance to incoming surges that we did in the old days when we used a different semiconductor device. So again, good question.
In regards to generator sizing, what percentage of harmonics is too high for the generator and cause it to fail or not start?
As far as the...
Go ahead, Dan.
I was going to say, as far as the current distortion is relative to the actual load itself on the generator. So as a percentage of the generator size, 20 to 30% of the load may be not as big of a deal as you might think. But as far as the voltage distortion, as you increase the voltage distortion, it's not so much the actual percent THD, and some people will say 5%, 8%, 10%. It's more about how it distorts the voltage, and with regulators and things as they are, the controls that are on the generator, if they don't see enough of a clean sinusoidal voltage coming out of that generator, the feedback that comes in, I've seen generators operate with 30% voltage distortion on an oil platform, but I've also seen them operate with 10% distortion and have problems with regulators. So it's more around the controls that go into the generator. Go ahead, Ed.
That's good. Next question.
Okay, can you discuss requirements for 4-wire input to UPS bypass with 3-wire loads?
Another good question, and I'll try not to make the answer too long-winded. Keep in mind you can contact me or Dan directly at the emails that are showing on the screen now. But the question was, if I have a 3-wire service to the bypass, and when would I maybe need a 4th wire or a transfer switch that operates with 4 poles? In other words, a pole for each of the 3 phases plus the neutral. And how does that impact the critical load? It's a good question to ask the UPS vendor and the automatic transfer switch vendor. But in a 480-volt system, it's kind of uncommon to see the neutral being required to support critical loads directly on the output. 277 volts phased in neutral is not commonly used in data centers, for example, but it might be used in something like emergency lighting. So that means that I need to have a continuous neutral all the time, even during the switching of the automatic transfer switch, in order to avoid dropping those 277 volt loads. It's much more common in a 208-120 system to have 120 volt loads that again require a continuous neutral even during switching operations to ensure that the 120 volt loads have a return path for their current and can continue operate during those switching. So if I have a transfer switch that has a 4th pole or a neutral pole, in many cases the user is not going to desire to connect the 2 different neutrals together because they're trying to avoid circulating currents. So that means the neutral may have a make before break arrangement just like the phase wires do. So that means that the UPS that is running on battery while the generator is starting, for example, needs to be able to create its own current carrying neutral to handle that return current. So those kind of questions need to be asked of the UPS vendor and the transfer switch vendor. There's lots of different ways to configure your transfer switch. You may have an overlapping neutral where the 2 source neutrals are tied together temporarily, or more likely you will have a break before make neutral so that you avoid any circulating currents like that. But that does mean the UPS has to be able to supply a neutral during that break.
And if I could just add a real quick comment to that, Ed, the cost benefit of going with a 3-wire input and output and then putting an isolation transformer on the secondary to feed maybe a smaller, maybe 5 or 10% of your load if it's lighting or something else, then certainly makes a lot more cost benefit than when going with a 4-wire transfer switch and all the extra work and potential issues that you have with it, as you mentioned earlier, if it's only a small amount of load.
Right, that's a better solution.
This is kind of a related question. This is for Ed. You mentioned in an earlier slide about switching neutral for ATS operation. The viewer wants to know, do you mean a 4-wire versus 5-wire system?
Yeah, that was exactly what we were talking about. A 5-wire would be 3 hot wires plus a neutral and, of course, ground for safety. And there's the good news is the transfer switch vendors, no matter who they are, typically offer a lot of options. You can offer an overlapping neutral that we talked about, or you can offer a delay time, the amount of time that the neutral overlaps or the amount of time that the neutral breaks as the switch actually transitions from one source to the other. So those are the kinds of features that I would recommend discussing with the automatic transfer switch vendor to make sure that those kinds of things are adjustable, just to make sure that the automatic transfer switch and the generator and the UPS are all in agreement as to how to handle this switching of source, because we're talking about in a typical transition where the UPS is running from utility power and the neutral from the source may be passing straight through the UPS to support the critical load, and then that incoming power fails. So now we're using the neutral that the UPS generates to support the critical load, and then the transfer switch changes over and provides yet a third neutral in this system in a relatively short period of time. So the neutral hops 3 times. Can the critical load tolerate that? A very good question, and as Dan mentioned just a minute ago, if you go ahead and invest in an isolation transformer downstream of the UPS, then that neutral would never change from the critical load's perspective. And remember, if you use a power distribution unit in a 480 volt environment and the PDU steps you down to 208, 120, that's exactly the benefit you get in that case.
Are there wireless solutions for battery monitoring? For example, a sensor that attaches to the battery and sends info to a receiving unit?
Yes, there are, and those are very attractive. If you've ever installed a battery monitoring system or seen one installed, it reminds you that it's a good time to have spaghetti for dinner because there is a lot of small gauge wiring that's involved, and if any of it is disconnected, then the system is compromised. So a wireless method of communicating from each battery jar or cell to a sensor that can then convert that to a data stream is a very attractive option and is available from a couple of different battery monitoring vendors. Keep in mind that UPS battery cabinets are notoriously electronically noisy, so you have to have a very robust wireless communication system that will not get fooled by electrical noise. But those are a very desirable feature in a battery monitoring system, yes.
What is the best tool to measure generator harmonics in the field?
I'll address that a little bit. I think there's several that you could use, including some of the monitoring that goes with the generator system or the UPS systems themselves, or actually with our power system monitoring. But the power expert meters that we put on switchboard, switchgear, and the upstream equipment today has every bit the capabilities of the Dranitz and Fluke and all these other portable power quality instruments of yesterday. So what I mean by that is long-term kind of monitoring for trending and analysis, and keep in mind that harmonics are not an instantaneous problem. Generally, they're more of a trending issue. So the 519 addresses that with statistics around how long are the harmonics on the system, and with most loads in the data center environment, you're going to have a fairly continuous amount of harmonics, but you can trend with those types of instruments and look at the voltage and current at the same time, and the harmonic voltage and current distortion at the same time, as well as any waveforms for anomalies that are caused that are transient in nature, including things like transformer inrush and all those kinds of things. So today you have a lot of options for monitoring harmonics, but the key is, again, that harmonics are more of a continuous or at least a longer-term problem. So as you want to take snapshots for THD and for voltage and current, you also want to take some trending information and see how things are changing over time.
Well, look, that looks like that's all the time we have for questions today. Please join me in thanking our presenters, Dan Carnovale and Ed Spears, for their presentation, as well as our sponsor, Eaton. If you have any additional questions or comments, please don't hesitate to click the email us button on the console. As you exit today's webinar, please take a couple minutes to complete our survey. We strongly welcome your detailed comments. Please visit webinars.missioncriticalmagazine.com for the archive of this presentation, as well as information about our upcoming events. We appreciate your time and hope you have found this webinar to be a valuable experience.